where there's 2 shear walls, but the questions have like, what if there's like 3, 4, 3 or 4. So let me, I think I will explain this one, and then I will have you work on one of these, and then I'll walk around and get questions. But anyway, so let's start with section 2 example. So again, the idea is you have a building like this, some sort of wind pressure or some sort of lateral force is working, and parts of it will go to the roof, and some parts of that roof lateral force would go to this shear wall. So that's kind of what's diagrammatically shown on this isometric view. So, and I'm showing only parts of this. So that's the diaphragm, roof diaphragm, which I'm showing as, it's supposed to continue, but I'm just showing parts of it with some sort of linear, some sort of a lateral force all the way along this wall. But anyway, and then the shear wall is shown like this, right? So this is the elevation of the diaphragm and drag strut, which is the beam beneath the diaphragm. And then there are 2 shear walls in this case. And then let's assume that the total of the lateral force that is carried by the tributary of this diaphragm is 6,000 pounds. So for the result of whatever calculation that I'm going to show you Wednesday, right? We got this fact that there's a 6,000 pound lateral force working towards the left onto this diaphragm, which is going to be carried by this drag strut and then ultimately be carried out by a shear wall, and shear wall gets pushed and it tries to resist that by tension and compression, right? So it's the lateral force is going to try to overturn this shear wall, and the shear wall is going to try to resist that by doing the opposite. Anyway, so we're really zooming into this drag strut part, and so what happens is on this beam, depending on where the lateral force hits, it's sometimes in compression, it's sometimes in tension. So that's why we need to kind of reinforce this beam. So this beam actually needs to be able to take compression this way and tension in this way. And in figuring out how much force this beam needs to resist, we need to kind of figure out how much force is working at each point of this beam, where the max and where is the maximum compression and where is the maximum tension, and that way engineers can figure out the worst case to design to, right? So that's basically the idea. So we are trying to draw this diagram, which is called, I think it's linear shear diagram. But basically, we are trying to plot a shear that's in this beam at every location, all along the entire length of this beam. So the way to read this explanation is actually I'm starting from here. And that's the diagram that's resulting, but we're gonna follow step by step, going downwards from here, and then this will explain that part, and so that's the last part. But anyway, so if you remember, right? So this diaphragm, so this is kind of what's called the free body diagram of this lateral force resisting system. I'm basically just taking this diaphragm, drag strut, and shear walls. I'm separating them so that I can look at each of them separately. But what we are really zooming in towards is this: what's in this beam, right? So that's what we are trying to analyze. And the question, typical question in your homework would be: at which point this beam experiences maximum compression and maximum tension? And it tends to be, actually, it's always going to be at these points, right? It's usually not in the middle of this beam or middle of the beam there. So And if you go to the Google form, you have the drop down of picking point A, point B, point C, point D for like maximum tension, maximum compression. In some cases, like the first example, it only experiences compression. So in that case, there's no point that this beam that experiences tension and stuff. But anyway, so that's the question, and I'm gonna begin my explanation, right? So far so good? Makes sense? Yeah? Okay, so right now, the lateral force is hitting this diaphragm from the right, trying to push it to the left side, right? So anyway, so we need to determine what's positive and what's negative so that we can start plotting, right? So so that's kind of something that you need to assume in the beginning, but we're gonna treat the leftward force, so in this case that one that's going this way, as positive, and whatever is on the other side, going towards the other side, is negative. So if you see a force like this, that's positive. If you see a force that's going the other way, which is this one, that would be negative. Anyway, so the positive force will hit this one, right? So we calculated unit shear for two cases. One is between the diaphragm and the drag strut. The other is between the drag strut and the shear wall, right? So what's happening is that this beam is really kind of in between, right? It's kind of like, I mean, I'm not going to use an analogy, but you've been in a position where one people tell you one thing and anyway. So it's kind of in this like awkward position of like being pushed in one direction by one guy, being pushed into the other direction by the other guy. So it's really going through a lot of it's going through a lot. Anyway, so this guy, so first of all, we are just going to look at what's going on between lateral force, the diaphragm and the drag struts. So that's the only thing that matters now. So if you look at those two only, right, the diaphragm and drag strut is connected at every location in this entire length, right? So it's like the beam is touching the diaphragm at all edges. So anyway, so this tries to go this way because it's being pushed by this guy. So this wants to go this way, but this doesn't want to move, right? So as a result, the beam experiences this linear shear. So between these two, it experiences shear of this direction because the diaphragm is basically trying to push this guy this way, right? In order to calculate the unit shear, right, we basically take this force. The diaphragm wants to move to the drag strut to the left, and the total force is 6,000 pounds. And if you kind of try to analyze each point of this beam moving towards the left, right? I mean, we want to calculate, it gets like, so this guy it starts to be pushed at the very end, but at that point, it's experiencing not much, but it continues to be pushed throughout its entire length, so it's going to accumulate this shear. So that's why we're kind of trying to calculate this unit shear, is like how much it's being pushed per linear length, right? So the unit shear in this case is Vmax, which is 6,000 divided by the entire length of this contact area between diaphragm and the drag strut, which is 40 feet. So therefore, the unit shear, I'm calling it V roof because it's on the roof side, is 6,000 divided by 40, and therefore the unit is important again. It's 150 pound per foot. So there's 150 pound of this shear force that's pushing this guy per every feet. So that's the unit shear for the roof side. Now, if we forget that part and just look at what's in between the drag strut and the shear wall. So now, so the diaphragm was trying to move the beam this way, but at the end of the day, it's not really moving because the shear wall is pushing back to the other direction, right? So it's really these guys that's doing the job of resisting that lateral force. So now this guy is kind of caught in between, right? You know, this wants to move it, you know, this wants to push it back to the other side, so that's negative towards the right. And then, so wherever it's touching the shear wall, that's what's happening. But if you look at the overall picture, the total force that's pushing this to the left was 6,000. So whatever that's pushing back also needs to total to 6,000 in the other direction, right? So it's actually like negative 6,000. Because if there's more force that's pushing it towards the other way, then the building has to move the other way, right? And you've never seen that. So always it's equal, right? So in order to calculate the unit shear, again, it's about the contact area between the wall and the beam, right? So if you calculate, if you look at where the wall is touching the beam, it's only in this length plus that length. So what matters is the total linear length of the contact between shear wall and the drag strut. So basically the unit shear calc is, keep in mind it's negative, right? Because it's the other direction. So negative 6,000 divided by, it's 10 feet and 15, so it's 15 plus 10, right? So negative 6,000 divided by 25, it results to minus 240 pounds per feet. So that's what I'm calling V wall, because that's the unit shear for the wall side. So that makes sense so far, right? So whatever is going on here, the unit shear is minus 240, and whatever is going on here, unit shear is positive 150. So if we analyze each location of the beam, there's only two scenarios. One, so this green actually covers this entire green, right? So if you look at the area between point B and point C, there's no shear wall, right? But the diaphragm is touching the beam. So wherever this thing is, so this green area, there's only unit shear between the roof and the drag strut. So only V roof is present at this green area. If you look at the other locations, either between point A and B or between point C and D, this purple area always has the unit shear on the roof side, but also the unit shear on the wall side. So there's actually never a point where only the unit shear on the wall side is present. It's either only the V roof or V roof and V wall is working at the same time. So in the purple area, there's V roof and V wall working at the same time. So that's based on that, right? So now we need to draw this diagram of how this unit shear accumulates. So therefore, we're gonna look at, so we only have two scenarios, the green zones and purple zone. So we're gonna look at the simpler one, which is the green zone first. So to determine the slope for this graph, let's say in this portion, which is between B and C, only V roof is working. So therefore the unit shear on this drag struts at that part is positive 150 pound per feet. And so here in this little box, I'm trying to plot this graph it's basically every unit, every feet that you move towards the left, you're gonna accumulate 100 pound force. So that's kind of, so I just, because I called the left facing arrow positive and right facing arrow negative. So that was positive 150. So it's going to go up. So it's going to go towards left 12 inches, and it's going to go up 150 pounds. And I just needed, so what scale you use here doesn't matter too much. The only thing that you need to be careful of is two things that you need to be careful of. One is, once you pick that scale, you should be consistent throughout the problem, because if you change the scale, then the graph reads differently, right? So you have to, you can pick whatever scale, but you have to stick to that. Second point is that that scale wants to be reasonable so that you can draw this diagram within the readable portion, right? Because like I wanted this graph to be readable and not like, I don't want this graph to be super deep like that. And one, it's extremely hard to draw and extremely hard to read. So it has to be somewhat a reasonable scale. So that takes some trial and error. But I arrived at, okay, if I draw 150 pound as 3 inches, that's gonna make my graph more or less at the reasonable scale. So that's some, I mean, you can stick to the scale, or you can figure out what the scale you want to use. So those are the only two criteria. One, it's easy to read the diagram, easy to draw the diagram. Two, you have to be consistent throughout. So in this case, I'm just using 3 inches equal 150. It happens to be 1 inch equal 50 pound. Anyway, so this part is straightforward, right? So it's only, so you move 1 foot this way and then 3 inches up. So that's going to be the slope of this graph for the green portion, right? And now we want to figure out the slope for the purple portion, which I'm going to try to show on this end, right? So the purple portion, right, between point A and B, where it's right here and here, between C and D, B roof and B wall, both of them are working. And according to the previous calculation, B roof was positive 150, B wall was negative 240, right? So because both of these guys are present at this purple location, the unit shear for this purple part is actually 150 minus 240 equals minus 90 pounds per feet, right? So therefore, using the same scale that I just used, which was 1 inch representing 150, if I want to represent negative 90, it needs to be minus 1.8 inch. So again, the slope for this graph is you move 12 inches to the left and move down 1.8 inches. So that's the slope for purple portion. So then this graph right here, it's basically, so if you read this, so the green part, that slope applies, and purple part, that slope applies. So I'm just kind of copying these sloped lines up there, and really what shows up is a, so for the purple part, right, you have this, sorry. So for the purple portion, I'm showing this downward slope, which I plotted down there. For the green part, I have this upward slope that I just copied from down there. So it always starts from 0, right? And because its purple portion is downward slope, it goes down. And whenever it gets to the green portion, it's going to start going up. And then back to the purple portion again. So it has the, so if you notice, that slope must be parallel to that slope, right? and it always goes back to 0. So if you started the graph and completed the graph and it didn't end at 0, you have miscalculated something. But anyway, so far makes sense, right? Plotting the diagram, negative and positive. So then the way to read this diagram is whatever is negative actually happens to be in tension. Whatever is positive happens to be in compression. And if you actually kind of try to visualize this, right? This actually, I wish I had some sort of a physical model, but you can imagine how that wall, because this guy is trying to move this way, right? So what's happening? So this guy is trying to move this way, and this guy is trying to stay there. So it kind of makes sense that this portion of that drug struts, that portion is being pulled away, and so the tension is accumulating up to point C, where the shear wall ends, right? So the tension is maximum at this end point of the shear wall, and it keeps going. So from here you don't have the shear wall, so the diaphragm keeps pushing this beam, so it's actually starting to express, so because it's being compressed, the tension starts to decrease, and at some point it turns into compression, and it reaches maximum compression where it hits this shear wall, right? And then because the shear wall pushes back again, the compression decreases and decreases, and it goes back to 0. So in this case, point B experiences maximum compression, and point C experiences maximum tension. So you actually kind of have to design this beam to be able to resist the tension of that amount and compression of that amount. Because what can happen is, this is not always, this is like this really abstract scenario where the lateral force is only hitting from one end, right? But earthquake doesn't really choose direction. So if it, so you have to think of this scenario, but it can also be pushed from the other end, right? But also, earthquake moves around. So, I mean, this is only looking at the shear wall in one direction, but then also the building moves around. So there's got to be other shear walls going towards the other direction on this building. But we're just looking at this wall. So we have to assume it can be pushed from this way or that way, right? So far it makes sense? Yeah? Okay. So, and that's why actually, so all of the problems, so there's like, two parts to this. So there's all these 4 problems up, and in the lower half you have almost the same exact problem, but I have this problem where you have the same exact shear wall configuration where the force is pushing from the exact opposite direction, just to kind of illustrate that point. But anyway, so that was kind of the detailed explanation of how to draw that diagram. So maybe so this one just has 4 walls. It just ends up being a little more, and it's just a little more cumbersome. So let's do, I think we did this one last week. So why don't we try to do section 2, question 3, right? So then you can kind of